Okay, now we're in part 3 of 5.2, and we're talking about local behavior of polynomial functions. A turning point of a graph is a point at which the graph changes direction from increasing to decreasing or decreasing to increasing. The y-intercept is a point at which the function has an input of the value 0, and x-intercepts are the points at which the output value is 0. And we already knew that about x-intercepts. And y-intercepts. So given a polynomial function, determine the intercepts. So the first thing you do is determine the y-intercept by setting x equal to 0 and find the corresponding output value. To determine the x-intercepts, by solving for the input values that yield an output value of 0. And then I just want to illustrate on the graph. Here are the zeros, or the x-intercepts. The y-intercept is where it crosses the y-axis. X-intercepts is where it crosses the x-axis. The opposite coordinate is 0. The turning point is where it changes direction. So here the graph is increasing, and now it's decreasing. So here's the turning point. Same thing here. It's decreasing, now it's increasing. There's the turning point. So given the polynomial function written in factored form for your convenience, determine the y and x intercepts. So to find the y-intercept, we're going to set x equal to 0. So we're going to rewrite this whole expression and find f at 0. So 2 times 0 minus 1 times 0 plus 2 times 0 minus 3. And we're going to put in 0 everywhere we see an x. So that yields 2 times negative 1 times 2 times negative 3. So f at 0 is 2 times negative 1 is negative 2 times 2 times negative 3. So that is f of 0 equals negative 4 times negative 3. And f of 0 is equal to positive 12. For the x-intercepts, we set the y, or in this case the f of x, equal to 0 and solve. So 0 equals 2 times x minus 1 times x plus 2 times x minus 3. And they said it was factored for our convenience. And what makes this convenient is that because we've set it equal to 0, then we know that one of these factors must equal 0. So either x minus 1 equals 0, x plus 2 equals 0, or x minus 3 equals 0. If we solve each one, we get x equals 1, we get x equals negative 2, and we get x equals 3. So we have the x-intercepts of 1, 0, negative 2, 0, and 3, 0. And we have the y-intercept of 0, 12. Okay, so your turn to try it. This, because you can't see it very well, that's a 3. So that's 2x to the third minus 6x squared minus 20x. So determine the x-intercepts and the y-intercept. Unpause when you're ready to go over it. Okay, so going over it, we want the y-intercept, and we're going to set the x equal to 0. So f at 0 is 2 times 0 to the third minus 6 times 0 squared minus 20 times 0. And honestly, what happens is it zeroes out. So our y-intercept is the point 0, 0. Okay, for the x-intercept, you set y equal to 0, or f of x equal to 0. So 0 equals 2x to the third minus 6x squared minus 20x. And we're going to solve by factoring because I can look at this and I can tell that a 2 will go in all three terms as well as an x. So if I factor that out, that would leave x squared minus 3x minus 10. And then 2x times x squared minus 3x minus 10 would factor into two binomials, x being the lead of each. Then the factors of 10, here on the end, that you would multiply to get 10, but add to get the middle term, which is negative 3. What would those be? So 2 times 5 is 10. We want negative 10. If we make it negative 5, 2 times negative 5 is negative 10. 2 plus negative 5 is negative 3. So plus 2 minus 5. So then we're going to take each of the factors, 2x, x plus 2, and x minus 5, and set them all equal to 0. And we'll get 0, negative 2, and 5. So for our x-intercepts, we have 0, 0, negative 2, 0, and 5, 0. Okay, so comparing smooth and continuous graphs, intercepts and turning points of polynomials. So this is important right here. So I'm going to highlight it. A polynomial of degree n will have at most n x-intercepts and n minus 1 turning points. So let's say, well, let's just look at a parabola. Well, we know the degree of a parabola is 2, so that means it's going to have at most 2 intercepts, n intercepts 2, and then n minus 1 is the number of terms. So 2 minus 1 is 1. It would have 1 turn. Now, notice what it said here. It has at most n x-intercepts and n minus 1 terms. It doesn't mean that we'll definitely have that many. Now, for a squared regular quadratic form, for a regular quadratic equation, this is accurate. But if you have a polynomial function, and let's say the degree is 3, that doesn't mean that you'll have 3 x-intercepts and 2 turns. It means that you can have at most that. So let's look at this example. It says, without graphing the function, determine the local behavior of the function by finding the maximum number of x-intercepts, max number of x-intercepts, and turning points. So all you have to do is look at your leading coefficient, or your leading term. So we have negative 5x to the 10th. So in this case, n equals 10. So that means that you can have at most 10 x-intercepts, and then turning points you can have up to 9. Because we do n minus 1. So your turn, try it without graphing, determine the maximum number of x-intercepts and turning points, and when you're done, unpause the video and we'll go over it. Okay, so it looks to me like, I could put these in order, but it looks like the highest degree is 12. Because the other degrees are 9, 4, and 3, and 0. So looking at 14x to the 12th, n is 12. That means there is at most 12 x-intercepts. That means we have 11, up to 11 turning points. And that's all you have to do there. Alright, so what can we conclude in this example about the polynomial represented by the graph shown? So, if we look, we have one x-intercept. So that would imply that n equals 1. But you have 1, 2, 3, 4 turns. And if you have 4 turns, that means that your degree, your n, would be 5. So based off of this here, I conclude about the polynomial that the degree is at least 5 because there are 4 turning points. Now there's only one X-intercept, but again, if you look back up here, it said a polynomial of degree n will have at most n X-intercepts and n minus 1 turning points. So it doesn't mean that if you only have one X-intercept that the degree is 1. So it means we could have up to, in this case, it looks like we'd have up to 5, but there was only 1. Now, so I would say that the minimum degree would have to be 5 since there are 4 turning points. So you guys try this one. Unpause when you're ready. Alright, so looking at X-intercepts, we have 3 X-intercepts. We have 2 turns. If we have 2 turns, that would imply that n equals 3 as well. So I think that the degree is most likely 3, or at least 3. Alright, so drawing conclusions about polynomial functions from the factors. So given the function, determine the local behavior. So it looks like if I were going to find the X-intercepts, I would set 2x equal to 0, x minus 2 equal to 0, and x plus 3 equal to 0. And I would get x equals 0, x equals 2, x equals negative 3. That means I have 3 X-intercepts. So, I'm sorry, that means we have a degree of 3 and up to 3 X-intercepts. That means how many turns can we have? If it's always n minus 1, so 3 minus 1 would be, oops, I wrote 2. 3 minus 1 would be 2 turns. Yeah. Alright, so you guys try this last one, and then we will go over it. Alright, so it looks like I'm going to have 3 X-intercepts. So if I have 3 X-intercepts, that means the degree is at least 3, and that means turning points. I have 1 less than that, which would be 2. Okay, and it looks like that's it for 5.2. Let me know if you have questions.